Okay, so where we left off before the exam was we were going to talk about properties. We talked about enthalpy. And today what we're going to do is talk about something called specific heat capacity, or heat capacity in general, what we're talking about. So let's talk about heat capacity. Okay. Heat capacity is going to be defined, we're going to write that as a capital letter C for heat capacity. Okay, and heat capacity is defined as the energy required to raise 1 unit of mass 1 degree. 1 degree. So it's either a kilogram, 1 degree Celsius, or a pound mass, 1 degree Fahrenheit. Okay, that's what it is. And not every substance has the same amount of energy required to raise a unit of mass 1 degree. Or this could be also say the energy required to be removed to lower the temperature 1 degree. Everything has a different value of this. Okay, that's called heat capacity. And we often talk about this as specific heat capacity. And you might have heard it already in chemistry as just talking about specific heat. Okay, we often will say specific heat, and it's just short about specific heat capacity. Now notice there's this word specific. Whenever you've had specific in this class before, what has that meant? Specific volume, specific internal energy. It's the same idea about we're going to be dividing the heat capacity by the mass. So if we take the heat capacity and we divide it by the mass, we're going to have lowercase c, and we're going to call that specific heat or specific heat capacity. Okay, and it can be really looked at as saying the heat transfer over the delta T. That's kind of how we're going to be looking at heat capacity, and it's an intensive property. Intensive property is specific heat. Okay, now here's how this works, and my best example is pi. Okay, I've talked a lot about pi. We've talked about pi with refrigeration cycles. Let's just say now it's now season where your apple season. We're gonna get like a lot of good apples. They're sale at Dillon's. Apple, you make apple pie. Okay, you work all day, you get apple pie. You make a nice homemade pie crust. You put in the apples and the gooey filling, and you bake it for a while. My family has been watching the Great British Baking Show, and so we know exactly how to do this. We know how to blind bake things. We know everything about making apple pie. Okay, get it out of the oven, let it cool for a little bit, and then you're going to cut that nice. You cut it into eighths, nice piece of pie. You get that nice piece of pie. You put it on your plate. Okay, and it's hot, so you let it cool. You let it cool for a little bit more, and then you've been wanting this pie for such a long time that you put your fork into it and you put it into your mouth and you kind of touch it on your tongue and you think, oh, that crust is cool, and you put it into your mouth, and what happens? But that molten lava, which is inside of that gooey goodness of the apple pie, is now on your tongue, causing third degree, fourth degree, fifth degree burns. That's the scientific fifth degree burns. And you, with a mouthful of pie, are shouting out, heat capacity! Because that's what's happened here. You were tricked by the different heat capacity of the pie crust to that of that inner goodness, inner gooey goodness. There's different rates at which the heat was trying to come out of there. It came out of the pie crust much easier, lower the temperature much better, much faster than that gooey inside needed more energy removed to reduce the temperature. Okay, so that's my example of heat capacity and how it deals in everyday life. And I hope the next time you burn your tongue on something, or the roof of your mouth, or whatever, that you scream out as loud as you can, heat capacity. And then when things are over, people will ask you, why did you scream out heat capacity? And then you could explain to them everything that we're going to talk about here. And again, that's going to just endear you with your friends, your family, loved ones, people you're trying to impress. All sorts of things are going to come your way by talking about thermodynamics. Okay, now there are two types of heat capacity that we're going to deal with. It's denoted as C sub V for constant volume heat capacity. And it's denoted as C sub P for constant pressure heat capacity. Okay, now I want to know, or I want to talk to you about which one of these is larger and why. So we have to do a thought experiment here. Let's now have a container, a rigid container that's a constant volume. Let's put a gas inside of it. Let's just put air inside of it, okay? Let's add heat to that gas. What's going to happen? The temperature of that gas is going to rise. In fact, what's going to happen is as the temperature rises, it's going to increase the pressure inside of that container. You've probably dealt with this or seen this before and kind of understand what's happening there. So heat coming in, going to be increasing the temperature and the pressure of the container, but the volume is remaining constant. Now, a constant pressure heat capacity, that's going to be a situation kind of like our piston cylinder here. Now we're going to be heating this, but what's going to happen is we want constant pressure to happen. So in the situation where we had constant volume, the pressure built up. How are we going to have the pressure be released in the situation? Well, that piston is going to rise to keep the pressure constant. Okay, we're still adding heat. The gas is going to increase in temperature, but now the volume is changing to make sure we have a constant pressure. Which one of these situations is going to have a larger C sub specific heat, C sub V or C sub P? And the answer to this is C sub P is larger. C sub P is larger than C sub V. It always is, because the temperature is going to rise faster in that constant volume. In that constant pressure situation, some of the energy that you're going to be adding is not going to go directly into changing the temperature. It's going to be into causing that change in volume. So the energy is going into two different places. And so because of that, it can't be all into the change in temperature. So therefore, you're going to have to put more energy in to take care of that volume change and the temperature change. So therefore, C sub P is always greater than C sub V. This is a good FE exam problem, multiple choice thing they often ask you. This is important for us to know. Okay, so how do we define C sub P and C sub V? Well, C sub V is defined as the partial derivative with respect to U with T as we keep volume constant. And C sub P is defined as the change in enthalpy over the change in temperature as we keep pressure constant. Okay, this is how they're defined. Okay, remember, H is equal to U plus PV. All right, see, it has that pressure and volume into it. So it makes sense that when we're trying to have that constant pressure, we have that volume piece added to it. This du is just the internal energy, the molecules vibrate, the molecules vibration. This is how they are defined. But I'm going to tell you something, and I'm going to reiterate this multiple times. This is how they're defined, but this is not necessarily how they have to be used. We are going to give you a value for C sub P. We're going to give you a value for C sub V. But you do not have to always use the specific heat at constant volume in constant volume situations. And you do not have to use the specific heat at constant pressure in constant pressure situations. It is just how we defined or created these values. And that can be very confusing to students as we get started. And I'll start to elaborate on that in more lectures, and especially we talk about gases. But my example or my analogy to this is the idea of duct tape. Okay, I should go out in the hallway and get some duct tape. We invented duct tape. We called it duct tape. It's gray. It was invented for use for ducts, but we created it for ductwork. Okay, but just because that's how it was created, that's how it was defined, does not mean that that's how we have to use it. Now we can use duct tape for anything. We could use duct tape we can create clothing with duct tape. There's lots of interesting things. We could fix a variety of things. Duct tape is a great back hair removal. If those of you out there, that's a great way to do back hair removal. Um, just lots of things that you can do with duct tape. So not defined. It's defined. It's called duct tape, but that doesn't mean, oh, sorry, can only use it for ducts. No, we use it for lots of other things. Same thing happens with C sub B and C sub P. So please don't lock yourself into, I can't use it in constant pressure or I can't use it in constant volume situations. All right. One last thing before we end this lecture segment is we'll talk about the units of it. The units of C sub P equal the units of C sub V, and they're going to be in kilojoules per kilogram Kelvin, and that's going to be in the SI system, or they're going to be in BTU per pound per degree Rankine, and this is going to be in the English engineering units. Now, of course, sometimes we're going to talk about C sub P bar and C sub V bar. We'll talk about them on a molar basis. In SI, that's going to be in kilojoules per kilomole Kelvin. And in English engineering, it's going to be in BTU per pound mole degree Rankine in English engineering units. Now note here, because we have temperatures in the denominator, this could also be kilojoules per kilogram Celsius and BTUs per pound degree Rankine, because we're talking about per Kelvin and per Rankine. And the degree Kelvin and the degree Rankine are the same step size as that with Celsius and Fahrenheit. So those rules still apply here when we're talking about our units. Okay, that's where we will end talking right there, and we'll come back and talk some more about specific heat.